Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable wherever you are. Let your body settle into this space. Where in the world are you watching from? A quiet bedroom where the day is finally winding down? A cozy corner where you can let your thoughts drift? Wherever you are, you're welcome here. Tonight we're going to explore one of the most fascinating and gentle questions in all of cosmology. What if we're already inside a black hole? It's a question that reframes everything we think we know about the universe, our place in it, and the very nature of reality itself. We'll discover what black holes actually are beyond the dramatic portrayals, understand the mathematics that suggest this possibility, and contemplate what it might mean for the story of existence. It's a journey that spans from the smallest quantum scales to the largest cosmic structures, from Einstein's equations to the very edge of human understanding. But don't worry, this isn't going to be a terrifying plunge into cosmic horror or an anxiety-inducing revelation that undermines everything. Instead, we'll move slowly and carefully through the science, the philosophy, and the beautiful implications of this idea. By the end, I think you'll find that this question, rather than being disturbing, opens up a wonderfully peaceful way of thinking about our universe. We'll take our time with each concept, building understanding gently. If you enjoy these calm explorations of the cosmos, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for trusting these journeys into the unknown. So settle in, let your shoulders drop, take a slow breath and feel it fill your lungs. And let's begin our slow drift through this question. There's nowhere you need to be right now, nothing you need to do. Just listen and let the story of our possible black hole universe unfold around you like starlight. Let's start with what we think we know about black holes, because understanding the conventional picture is essential before we can explore how our entire universe might be one. For most people, black holes exist in imagination as cosmic monsters, terrifying voids that devour everything, points of infinite density where the laws of physics break down into incomprehensible chaos. But the reality, as always in science, is both stranger and more beautiful than the mythology. A black hole, in the traditional understanding, forms when a massive star exhausts its nuclear fuel and can no longer support itself against the crushing force of its own gravity. The core collapses, and if there's enough mass, nothing can stop the compression. What results is a region of space-time where gravity becomes so intense that not even light can escape from within a certain boundary. We call that boundary the event horizon. It's not a physical surface, not a membrane or a wall. It's simply the point of no return, the place where the escape velocity exceeds the speed of light. And this is where things get genuinely interesting. The event horizon marks a one-way door in space-time. Anything that crosses it, whether matter or light or information, continues inward and cannot come back out. Not because there's a barrier preventing exit, but because all paths through space-time inside the horizon point toward the centre. It's as inevitable as tomorrow following today. Once you're inside, moving toward the singularity isn't a choice, it's simply the direction that time flows. The singularity itself, that point at the centre where all the mass compresses to infinite density, is where our current physics genuinely breaks down. General relativity, Einstein's beautiful theory of gravity as curved space-time, predicts its own failure at this point. The equations return infinities, which in physics is usually nature's way of telling us we're missing something important. Most physicists suspect that quantum gravity, a theory we haven't fully developed yet, would smooth out this singularity into something comprehensible. But for now, it remains a mystery wrapped in mathematics. What's crucial to understand is that black holes aren't actually holes at all. They're not empty voids or tunnels to somewhere else. They're objects, incredibly dense concentrations of matter that have collapsed to a size smaller than what we call the Schwarzschild radius, the point where escape velocity equals light speed. For the Sun, if you could compress all its mass, that radius would be about 3 kilometres. For Earth, less than a centimetre. These aren't practically achievable compressions for objects that size, which is why they remain stable. But for massive stars at the end of their lives, this compression happens naturally, catastrophically, inevitably. And perhaps most beautifully from the outside, a black hole appears almost serene. Matter falling toward the event horizon seems to slow down as it approaches, its light stretching and reddening, until it appears to freeze just at the boundary, taking infinite time to cross. This is because of time dilation, the way time moves differently in intense gravitational fields. An outside observer never quite sees anything cross the horizon. But from the perspective of the falling object, the crossing happens in finite time, unremarkably in some ways, though marking the point beyond which return becomes impossible. This is the standard story of black holes. Refined through decades of theoretical work and increasingly supported by observations of stellar mass black holes and the supermassive ones at galactic centres, it's a story we're fairly confident about, which makes the question of whether we might be inside one all the more intriguing, because it requires us to look at this familiar picture from an entirely different angle. Now let's consider what the universe might look like from inside a black hole. Because this shift in perspective is where our question begins to take shape. If you were to somehow cross an event horizon while remaining intact, protected from the tidal forces that would normally tear you apart, what would you experience? What would the universe around you look like? The answers are counterintuitive and beautiful. First, and this surprises many people, you wouldn't necessarily notice the moment of crossing. The event horizon isn't a place where anything physical happens to you. No barrier strikes you. No force suddenly grabs hold. For a sufficiently large black hole, the one we'll discuss later, the tidal forces at the horizon could be incredibly gentle. You would cross from outside to inside as smoothly as crossing an invisible line on the ground. The change isn't in your immediate environment, but in the structure of possible futures available to you. Once inside, the nature of space and time exchanges in a profound way. Outside the horizon, you can move freely in any direction through space, but you're compelled to move forward through time. Inside, your movement toward the singularity becomes time-like, as inevitable as the ticking of seconds. You can no more avoid moving toward the centre than you can avoid moving into the next moment outside. Meanwhile, what we usually think of as time becomes space-like, something with direction and possibility. Looking outward from inside would show you something remarkable. The light from the universe you left behind could still reach you. Depending on when and where you looked, you might see the stars and galaxies, though distorted by the extreme curvature of space-time. In principle, you could watch the entire future history of the outside universe unfold in compressed time, though in practice, what you would actually observe depends on complex details of how light travels through the curved geometry. But here's what matters for our larger question. From inside, you would still see a universe around you. You would still have space to move through, for a time at least. You would still have matter and energy and light. The universe wouldn't disappear or become unrecognizable. It would simply be a universe whose future is constrained, whose overall structure is determined by the geometry of the black hole surrounding it. And this raises a gentle but persistent question. How would you know? If you found yourself in a region of space that appeared normal locally, how could you determine whether you were in an ordinary expanding universe or inside a black hole? What test could you perform? What observation could you make? The question isn't academic or abstract. It's deeply practical because it applies to us, here, now, observing our universe from within it. Consider that we observe an expanding universe around us. Space itself stretches, carrying galaxies away from each other. We see a cosmic microwave background, the afterglow of an early hot dense state. We measure the universe's age at about 13.8 billion years. We detect the effects of dark matter and dark energy shaping cosmic evolution. All of this fits beautifully into what we call the Big Bang model, a universe that emerged from an extremely hot, dense state and has been expanding and cooling ever since. But what if all of these observations could also be consistent with being inside a black hole? What if the Big Bang, that initial state, was actually the formation of the black hole as seen from inside? What if the expansion we measure is a feature of the black hole's internal geometry, rather than the growth of a standalone universe? These aren't wild speculations without mathematical foundation. They're questions that emerge from taking general relativity seriously and asking what it predicts about the view from inside an event horizon. The possibility challenges us to think more carefully about what we actually observe and what we infer from those observations. It reminds us that our perspective, our vantage point in the cosmos, fundamentally shapes what we can conclude about reality. And it suggests that some of the deepest mysteries about our universe, questions about why it began or what lies beyond its edges, might have answers that require thinking about structure and containment in ways we haven't fully explored. Let that thought settle as we continue, because we're going to build on this foundation carefully, examining both the mathematics and the philosophy of what it might mean to be inside rather than outside. To understand how seriously we can take this idea, we need to look at the mathematical description of black holes, starting with the simplest and most elegant solution. Just months after Einstein published his general theory of relativity in 1915, a German physicist named Carl Schwarzschild found an exact solution to Einstein's field equations. He did this while serving in the German army during World War I, suffering from an illness that would soon claim his life. His solution described the space-time geometry around a perfectly spherical, non-rotating, uncharged mass. What Schwarzschild discovered, worked out in the trenches with pencil and paper, was that if you compressed any amount of mass into a small enough region, something remarkable happened to the surrounding space-time. The geometry developed a surface where time and space coordinates switched their mathematical roles. This surface, the event horizon, sits at a distance from the centre that depends only on the mass. The more mass you compress, the larger this radius becomes. For the Sun's mass, about 3 kilometres. For 1 billion solar masses, about 3 billion kilometres. The relationship is perfectly linear and beautifully simple. But here's what Schwarzschild's solution also revealed, something that took physicists decades to fully appreciate. The geometry inside the event horizon is perfectly well defined. The mathematics doesn't stop or break at the horizon. It continues smoothly inward, describing a region where the future direction points toward the centre, where movement toward the singularity is inevitable, but where space and time still exist in meaningful ways. The interior solution is just as valid, just as real in the mathematical sense, as the exterior. For many years, physicists weren't sure whether these interior regions were physically real or mere mathematical artifacts. Could nature actually create such structures? Would they be stable? Would quantum effects eliminate them? But over time, through careful analysis and eventually through observations of real black holes in space, confidence grew that these interior regions do exist. When massive stars collapse, they don't stop at the event horizon. The collapse continues inward, creating a genuine interior. Now, the Schwarzschild solution describes an eternal, unchanging black hole. It's existed forever and will exist forever, a purely theoretical construct since real black holes form from stellar collapse at finite times in the past. But the mathematics of this eternal case reveals something profound about the structure of black hole interiors. In the Schwarzschild geometry, the interior connects to the exterior through the event horizon, but it also extends forward in time, encompassing an entire future region of space-time. And if you examine the global structure carefully, you find something even more intriguing. The Schwarzschild solution actually describes two exterior regions connected by a throat through the black hole interior. This throat pinches off, preventing travel between the two exteriors. But mathematically, the structure suggests a kind of doubling, a symmetry between an outside and an inside that mirror each other in particular ways. This feature, sometimes called the Einstein-Rosen Bridge before we understood it better, hints at the kind of structural richness that black hole geometries possess. For our question about whether we might be inside a black hole, the Schwarzschild solution matters because it demonstrates rigorously that black hole interiors are consistent, describable regions with their own geometric properties. They're not magical zones where physics ends. They're places where physics continues, albeit in a geometry where certain directions have different meanings than we're accustomed to. The mathematics works. The structure makes sense. The question is whether nature actually implements these structures on cosmic scales. What the Schwarzschild solution doesn't do, however, is describe an expanding universe. The interior geometry is static in certain ways that don't match what we observe around us. For our universe to be inside a black hole, we'd need a different kind of black hole solution, one with properties that match cosmic expansion, the presence of matter and energy throughout space, and the evolution we measure over billions of years. And it turns out such solutions exist. They're more complex than Schwarzschild's elegant simplicity, but they're equally valid mathematically. As we move forward, we'll explore these more elaborate geometries, but for now, appreciate what Schwarzschild gave us. Proof that black hole interiors are real places in the mathematics of general relativity. Regions where space and time continue to exist in configurations different from what we experience in ordinary space. This foundation supports everything that follows. Let's turn our attention now to the single most obvious feature of our universe. It's expanding. Galaxies recede from each other at speeds proportional to their distances. Space itself stretches, carrying matter along with it. This expansion is not an explosion of galaxies moving through space, but rather the growth of space itself, predicted by general relativity when you apply it to a universe filled fairly uniformly with matter and energy. The standard model of cosmology, what we call the lambda CDM model, describes this expansion beautifully, matching observations to remarkable precision. But could this expansion be happening inside a black hole? At first thought, it seems impossible. We tend to imagine black hole interiors as doomed, collapsing regions where everything crunches down toward the singularity. How could such a space be expanding? The answer lies in understanding that expansion and collapse can coexist in different directions, and that the global structure of space-time inside a black hole can be more complicated than simple compression. Consider first what expansion really means. When we say the universe expands, we mean that a particular measure of spatial distance, the distance between objects moving with the cosmic flow, increases over time. This is encoded in what physicists call the scale factor, a function of time that multiplies spatial distances. As time moves forward, this scale factor grows, and distances between freely moving objects increase. This happens not because objects are moving through space in the ordinary sense, but because the space between them is genuinely stretching. Now, inside a black hole, the inevitable future direction points toward the singularity. But the geometry of space at each moment of this inevitable future is not necessarily simple or uniform. You could have a situation where, as you move toward the singularity, the spatial slices, the three-dimensional spaces at each time, are themselves expanding. Think of it like this. You're on a train moving inevitably toward a destination, but the train itself is getting larger as it moves. The motion toward the end and the expansion of the train are two different compatible features. Mathematically, this is possible. You can construct solutions to Einstein's equations that describe black hole interiors containing expanding spatial geometries. These solutions require matter and energy distributed throughout the interior, providing the gravitational source that drives both the containment of the black hole and the expansion of space within it. The matter content has to have particular properties, matching what we call a cosmological fluid, matter with pressure and density related in specific ways. Remarkably, when you work through the mathematics carefully, you find that an observer inside such a black hole would measure an expansion rate, a Hubble constant, just as we do in our universe. They would see distant galaxies receding, would measure redshifts in the light from those galaxies, and would conclude that space is expanding. All of this would be genuine, not an illusion. The expansion would be real, happening in the spatial dimensions perpendicular to the direction toward the singularity. There's something profoundly important here. The expansion of the universe and the existence of a singularity in our future are not mutually exclusive. They can coexist. The universe can be expanding now, growing larger with each passing billion years, while still having an event horizon surrounding it and an ultimate singularity in the far future. The expansion doesn't protect us from that future. It simply describes what's happening to space right now. This resolves one of the first objections people raise to the idea. Quote, zero. The answer is that the terms expanding and collapsing refer to different aspects of the geometry. Spatial expansion and temporal progression toward a singularity are compatible features of a sufficiently complex black hole interior. General relativity permits, even predicts, such structures under the right conditions. What's more, the expansion we observe has been accelerating over the past few billion years, driven by what we call dark energy. This acceleration fits naturally into certain black hole interior models. The dark energy, which behaves like a cosmological constant, a kind of energy inherent to space itself, can exist in a black hole interior just as easily as in a standalone universe. It would have the same effects, the same observational signatures. So when we look out at the expanding cosmos, measuring its growth, detecting its acceleration, we're seeing something entirely consistent with being inside a particular kind of black hole. The expansion doesn't rule out the possibility. It merely tells us what kind of black hole geometry would be required, one with specific matter and energy content, one large enough that the time from horizon crossing to singularity encounter is billions of years, one with internal structure complex enough to match what we observe. And this brings us to a question that becomes increasingly important. If the math allows it, and observations don't rule it out, what exactly would make our universe a black hole? What would have to be true about the larger reality in which this black hole exists? We'll explore that question carefully, but first, we need to understand more about what observations actually tell us. Let's examine what we actually observe about our universe, looking at the data with fresh eyes, asking what it could tell us about our possible containment. We measure the universe in multiple ways, through the cosmic microwave background radiation, through the large-scale distribution of galaxies, through supernovae in distant galaxies, through the abundances of light elements formed in the early universe. Each measurement constrains our understanding. Each data point narrows the possibilities. The cosmic microwave background, that faint glow of radiation coming from all directions, shows us the universe as it was about 380,000 years after the Big Bang. At that time, the universe had cooled enough for electrons and protons to combine into neutral hydrogen, allowing light to travel freely for the first time. What we see in this radiation is astonishingly uniform, with temperature variations of only about 1 part in 100,000. This uniformity tells us the early universe was remarkably smooth, nearly homogeneous. But there are patterns in those tiny fluctuations, acoustic oscillations frozen into the radiation, the signature of sound waves travelling through the hot plasma before it became transparent. These patterns encode information about the geometry of space, the density of matter and energy, the conditions prevailing when the universe was young, and when we analyse them carefully they tell us that space is flat, or very nearly so on the larger scales we can measure. Flatness is a geometric property. It means that parallel lines remain parallel, that the angles of triangles add to 180 degrees, that space follows Euclidean geometry when you average over sufficiently large volumes. This flatness is not inevitable. Space could curve positively like a sphere or negatively like a saddle, but observations indicate that the curvature, if it exists, is extraordinarily small. The universe appears to be balanced precisely at the boundary between positive and negative curvature. This flatness is actually slightly puzzling in standard cosmology, because it requires extremely precise fine-tuning of initial conditions. The early universe had to start with a density extraordinarily close to what we call the critical density, the exact value that produces flat space. Even tiny deviations from this value would have grown rapidly, leading to a universe that's obviously curved today. The fact that we measure flatness suggests either a remarkable coincidence or some mechanism that set the initial conditions with great precision. Inflation, the hypothesis that the universe underwent a brief period of exponential expansion in its first fraction of a second, provides one explanation for this flatness. Inflation would stretch any initial curvature to negligible levels, like inflating a balloon until its surface appears flat locally. This explanation is elegant and widely accepted, though inflation itself raises questions about what caused it and what came before. But there's another way to achieve flatness. If our universe exists inside a very large black hole, the internal geometry could naturally be flat on the scales we can measure, while still being ultimately closed by the event horizon at much larger scales. Think of it like living on the surface of an enormous sphere. Locally, the surface appears flat. Only when you travel far enough do you notice the curvature. Similarly, our universe could be flat across all the scales we've measured. Billions of light years, while still being finite and bounded at scales we can't yet observe. The expansion rate we measure, the Hubble constant, also fits into this picture. We determine that space expands at about 70 kilometers per second per megaparsec, meaning that galaxies 1 megaparsec apart recede from each other at 70 kilometers per second. This rate has changed over cosmic history, faster in the early universe, slowing as matter's gravitational pull counteracted the expansion, then speeding up again in recent billions of years as dark energy became dominant. All of these measured values, the expansion rate, the matter density, the dark energy density, the spatial flatness, fit into a consistent picture. But it's a picture that's compatible with either a standalone universe or a black hole interior. The observations don't distinguish between these possibilities, because both predict the same local physics, the same evolution of expansion, the same formation of structure. The difference lies not in what happens inside, but in the global topology, the overall structure of space-time that surrounds us. One observation that might distinguish between the possibilities is whether space is finite or infinite. An infinite universe cannot be inside a black hole, because black holes have finite interiors bounded by their event horizons. But we haven't measured whether the universe is finite or infinite. We've only measured that it's very large, larger than the observable portion. The observable universe, the region from which light has had time to reach us, extends about 46 billion light-years in all directions due to the expansion of space. But the total universe could be much larger, potentially infinite, or it could be finite but still much larger than what we can see. If the universe is finite, particularly if it's finite in a way that matches the expected size of a black hole, interior given our observations of density and expansion, that would be consistent with the black hole hypothesis. If it's infinite, the hypothesis fails. But we don't yet know which is true. The data, as detailed and precise as it's become, hasn't answered this particular question, and so we're left with a possibility that remains open, neither confirmed nor ruled out, waiting for observations that might finally settle the matter. Let's explore now one of the most mathematically beautiful aspects of black hole geometry, a feature that connects directly to our question. In 1935, Albert Einstein and Nathan Rosen published a paper examining the Schwarzschild black hole solution from a new perspective. They were interested in whether these solutions might provide connections between different regions of space, what they called quote one through the geometry. What Einstein and Rosen discovered was that the mathematical structure of a non-rotating black hole contains more than just an exterior and an interior. When you analyse the complete geometry carefully, you find that it actually connects two separate exterior regions through a throat in the middle. Imagine two different universes, two separate expanses of space, joined by a narrow passage that passes through what we identify as the black hole interior. This passage, now called an Einstein-Rosen Bridge or sometimes a wormhole, is a natural feature of the Schwarzschild solution. However, and this is crucial, the bridge is not traversable. The throat pinches off faster than light can travel through it. If you tried to pass from... Before we continue, I want to pause for just a moment. Because what you have learned in the last 30 minutes is something genuinely rare. Most people move through their entire lives without ever stopping to understand the world at this level. But you did. Tonight you chose curiosity over noise and depth over distraction. That is exactly who this channel was made for. If you want to keep being that person, a like and subscribe takes 2 seconds and make sure this channel never stops finding you. Now, let's go deeper. If you tried to pass from one exterior to the other through this bridge, you'd get caught in the interior and reach the singularity before making it through. The two exteriors are connected mathematically, but causally separated. Nothing can actually travel between them. This dashed Einstein's hopes of using these bridges to explain elementary particles, but it revealed something profound about the structure of black hole spacetimes. The existence of this bridge, even though it's not traversable, tells us that black hole interiors have an inherent duality. They separate two regions while also connecting them. They're simultaneously boundaries and interiors, divisions and unifications. This mathematical property has deep implications for how we think about what underscore quote underscore 2 underscore means in the context of black holes. Now, when physicists began studying more realistic black holes, ones that form from collapsing stars rather than existing eternally, the picture changed somewhat. A black hole formed from stellar collapse doesn't have the full Einstein-Rosen bridge structure. Instead, it has a single exterior region, the universe in which the star collapsed, and an interior region that's causally connected to that exterior's future. The interior is real and physical, but it doesn't bridge to another exterior. Yet the mathematics still reveals interesting structure. The interior of even a realistic black hole has a geometric richness that goes beyond simple compression. There are horizons, regions with different causal properties, and a progression from the event horizon to the singularity that takes time, during which spatial expansion or contraction can occur. The interior is not a point. Not instantaneous. It's a region of space-time with volume and duration. And here's where things get interesting for our question. If we imagine our universe as the interior of a black hole, we need to ask, a black hole in what? What is the exterior region? Is it another universe? A parent space into which our universe black hole is embedded? This is where the mathematics starts suggesting possibilities that stretch conventional thinking. One proposal, explored by various physicists over the decades, is that universes might spawn from black holes. When a black hole forms in a parent universe, the interior might develop into an entire expanding universe of its own, causally disconnected from the parent. This new universe would have its own physics, its own particles and forces potentially, determined by the conditions of the black hole's formation. The event horizon would separate the two universes absolutely, preventing any communication or influence. From inside this black hole universe, observers like us would see expanding space, galaxies, cosmic microwave background, all the features we actually observe. We would have no way to detect the parent universe or the event horizon surrounding us, because we've always been inside, because the light from the parent universe either never crosses the horizon or gets infinitely redshifted by the time it reaches us. We would simply see our universe as it is, complete and self-contained from our perspective. From the parent universe's perspective, the black hole would appear as a dense object with mass equal to all the matter and energy in our universe. Time dilation would mean that while billions of years pass for us inside, far less time passes outside. The entire history of our universe, from Big Bang to ultimate end, might occur in a relatively brief period from the exterior viewpoint. This is one of the strange consequences of how time works differently in different gravitational environments. This picture of universes spawning from black holes is speculative but mathematically consistent. It's been explored seriously by physicists including Lee Smolin, who proposed a cosmological natural selection hypothesis where universes that form many black holes produce many offspring universes, leading to evolutionary dynamics on cosmic scales. Whether this actually happens in nature is unknown, but the mathematics of general relativity permits it. What matters for our exploration is recognizing that black hole interiors can have the structure and properties of entire universes. The mathematics supports this. The physics allows it. The question becomes not whether it's possible, but whether it's actual, whether the universe we inhabit is one such interior or something else entirely. To understand how an expanding universe can exist inside a black hole, we need to look at the equations that describe cosmic evolution. These are the Friedmann equations derived by Alexander Friedmann in the early 1920s, just a few years after general relativity was published. These equations govern how the scale factor of the universe changes over time, relating the expansion rate to the density and pressure of matter and energy filling space. The first Friedmann equation looks deceptively simple. It relates the square of the expansion rate, what we call h squared, to the density of matter and energy, plus a term for spatial curvature, plus the cosmological constant. The second equation relates the acceleration of expansion to the density and pressure. Together, they completely determine how a homogeneous isotropic universe evolves, meaning a universe that looks the same at every point and in every direction on large scales. What's remarkable is that these same equations can describe the interior of a black hole if that interior contains matter and energy distributed uniformly. The mathematics doesn't distinguish between a standalone universe and a black hole interior, as long as the conditions of homogeneity and isotropy hold. Both cases are solutions to Einstein's field equations. Both evolve according to the same Friedmann dynamics. The difference lies in the boundary conditions, the global structure surrounding the evolving space. In a standalone universe, we typically assume there's no boundary, that space extends infinitely, or wraps around on itself in a finite but unbounded way. In a black hole interior, there's a definite boundary, the event horizon surrounding the space. Inside that boundary, the Friedmann equations still apply. Space still expands according to the same rules, but the overall structure is contained within a larger space-time. Let's work through what this means concretely. Imagine a black hole massive enough that its interior could contain something like our observable universe. The mass would need to be enormous, perhaps 10 to the 53 kilograms or more, which is roughly the mass of the observable universe. This would create an event horizon with a radius of tens of billions of light-years, comfortably larger than the 46 billion light-year radius of our observable region. Inside this horizon, you could have matter and energy distributed roughly uniformly, with density around 10 to the minus 26 kilograms per cubic meter, which is what we measure in our universe. This matter would curve space-time, and the curvature would cause space to evolve, to expand or contract depending on the balance of density, pressure, and cosmological constant. If the conditions are right, the expansion would follow exactly the history we've reconstructed for our universe: rapid early expansion. A period of slower expansion dominated by matter, and recent acceleration due to dark energy. The Friedmann equations would predict all of this, whether we're in a standalone universe or a black hole interior. The cosmic microwave background would form at the same time, when the density and temperature dropped enough for atoms to form. Galaxies would condense from initial density fluctuations on the same timescales. Stars would form, planets would coalesce, life might emerge, all following the same physical laws. The same evolutionary patterns, but there would be one crucial difference in the far future. In a standalone infinite universe with dark energy, expansion accelerates forever, eventually leaving each galaxy isolated in its own observable bubble as everything else recedes beyond the cosmic horizon. In a black hole interior, no matter how the expansion evolves, there's an ultimate singularity in the future. The interior cannot last forever. At some point, the geometry leads to a final state where space-time curvature becomes infinite. This singularity might be extraordinarily far in the future. For a sufficiently massive black hole, the time from horizon to singularity could be trillions of years, far longer than the current age of the universe. During that time, the interior could undergo all the evolutionary phases we observe and more. Galaxies could form and die, stars could burn through their fuel and fade, civilizations could rise and fall countless times, all before the ultimate end. The Friedmann equations, when applied inside a black hole, predict this eventual singularity as inevitably as they predict the expansion we currently observe. But the timescale depends on the black hole's properties. A more massive black hole, one with a larger event horizon, generally has a longer interior lifetime. The relationship isn't linear, but the principle holds. Bigger black holes have interiors that last longer, and here's something that gives pause. We don't know if our universe will end. The accelerating expansion driven by dark energy suggests space will stretch forever, becoming ever emptier and colder in what's called the Big Freeze or heat death scenario. But if we're in a black hole, there's a definite end, a singularity in the future that we cannot avoid. The current acceleration doesn't protect us from this fate. It merely describes what's happening now during this phase of the black hole interior's evolution. Could we tell the difference by observing more carefully? Could we detect signatures of the event horizon or the approaching singularity? The answers are subtle and require careful thought about what kinds of observations might reveal global structure. We'll explore those possibilities as we continue, but for now, understand that the Friedmann equations, the foundation of modern cosmology, work equally well whether we're describing a universe or a black hole interior. The mathematics is the same. The physics is the same. The question of which we actually inhabit requires looking beyond these equations to larger considerations. As we delve deeper into the physics of black holes and whether our universe could be one, we need to acknowledge the limits of general relativity and consider what happens when quantum mechanics enters the picture. General relativity, for all its predictive power and mathematical beauty, is a classical theory. It treats space-time as a smooth continuum and doesn't incorporate the fundamental discreteness and uncertainty that quantum mechanics reveals at small scales. Near a black hole's singularity, where space-time curvature becomes extreme, quantum effects should become important. The classical prediction of infinite density and curvature is likely an artifact of our incomplete theory. A complete theory of quantum gravity, which we don't yet have, would presumably replace the singularity with something else, perhaps a region of extremely high but finite curvature, or perhaps some entirely different structure that emerges from quantum space-time itself. But quantum mechanics also affects our understanding of event horizons, and this is where things get particularly interesting for our question. In the 1970s, Stephen Hawking discovered that black holes aren't perfectly black. Quantum effects near the event horizon cause black holes to radiate, to emit particles with a thermal spectrum. This radiation, now called Hawking radiation, means that black holes slowly lose mass over time, eventually evaporating completely. Hawking radiation arises from quantum fluctuations near the horizon. Normally, in empty space, particle-antiparticle pairs pop into existence briefly and then annihilate. Near an event horizon, one member of the pair can fall in while the other escapes, leading to a net flow of energy away from the black hole. From outside, this appears as thermal radiation with a temperature inversely proportional to the black hole's mass. Larger black holes are colder, smaller ones are hotter. For stellar mass black holes, this temperature is incredibly low, far colder than the cosmic microwave background. They absorb more energy from the universe than they radiate, so they grow rather than shrink. But in principle, if you waited long enough in an otherwise empty universe, Hawking radiation would eventually cause all black holes to evaporate. For a solar mass black hole, this would take about 10 to the 67th years. For supermassive black holes, even longer. These timescales are so vast they're almost meaningless in a practical sense. Now, what about a black hole containing an entire universe? If our universe is inside such a black hole, would Hawking radiation affect us? The answer is subtle. Hawking radiation is a process occurring at the event horizon, where quantum effects create particles that escape to the exterior. From inside, we wouldn't detect this radiation directly. It's generated at the boundary and flows outward into the parent universe. But the mass loss from Hawking radiation would change the black hole's properties over time. As mass radiates away, the event horizon would shrink. For a black hole universe, this might manifest as a change in the global properties of space-time, perhaps affecting the expansion rate or the approach to the final singularity. However, the timescales involved are so enormous, and the effect for a massive black hole so incredibly slow, that it would be undetectable over the billions of years we've observed. There's another quantum effect worth considering, the information paradox. When matter falls into a black hole, it carries information about its quantum state. If the black hole then evaporates via Hawking radiation, which is purely thermal and carries no specific information, what happens to the original information? Quantum mechanics says information cannot be destroyed, but the classical picture of black holes suggests it's lost. This paradox has driven decades of theoretical work. Recent developments in quantum gravity suggest that information is preserved, somehow encoded in the Hawking radiation in subtle correlations, or perhaps stored at the event horizon in holographic form. This leads to ideas like the holographic principle, which proposes that all the information in a volume of space can be encoded on the boundary of that volume. For a black hole, this means all the physics of the interior might be described by a theory living on the event horizon. If our universe is a black hole interior, the holographic principle might mean that everything we observe, all the matter and energy and structure, could be encoded in some form on the event horizon surrounding us. This is a strange and profound idea. It doesn't mean our universe is illusory or less real, but rather that there might be a dual description, an equivalent way of describing the same physics in terms of information on the boundary. These quantum considerations don't invalidate the possibility that we're in a black hole, but they add layers of complexity and suggest that the full story requires physics beyond what general relativity alone provides. A complete answer to whether our universe is a black hole interior might require understanding quantum gravity, reconciling the smooth space-time of general relativity with the discrete, uncertain nature of quantum mechanics. The fact that we don't yet have this complete theory means there are aspects of the question we cannot fully address. We can say what general relativity predicts, we can explore how quantum corrections might modify those predictions, but we cannot definitively answer all questions about singularities, about information, about the ultimate nature of space-time. This uncertainty is part of the frontier of physics, the edge where current knowledge meets the unknown. And perhaps there's something appropriate about that. If we are inside a black hole, we're in a region where the most extreme physics plays out, where space-time itself is pushed to its limits. It makes sense that understanding such a situation fully would require our deepest theories we're still developing. The question remains open, partly because our physics remains incomplete. Both will develop together as we continue exploring. Let's turn our attention now to one of the most mysterious components of our universe, dark energy, the force driving the accelerated expansion we've measured over the past few billion years. understanding dark energy is crucial for our question, because its properties significantly affect what kind of black hole could contain an expanding universe like ours, and what that would mean for our cosmic future. Dark energy reveals itself through its effects on expansion. In the late 1990s, two teams of astronomers studying distant supernovae discovered that the expansion of the universe was speeding up rather than slowing down as had been expected. This was shocking, because gravity should pull matter together. Decelerating expansion. The only way to accelerate expansion is if there's some form of energy with negative pressure. Energy that pushes outward rather than pulling inward. The simplest explanation for dark energy is a cosmological constant, a term Einstein originally added to his field equations to allow for a static universe, then later called his biggest blunder when the universe was found to be expanding. But perhaps it wasn't a blunder after all. A cosmological constant represents energy inherent to space itself, energy that doesn't dilute as space expands. Each cubic meter of space contains the same amount of dark energy, regardless of how the universe evolves. This constant energy density has a peculiar equation of state. Its pressure equals minus its energy density. This negative pressure is what drives acceleration. As space expands, more dark energy appears to fill the new volume, maintaining constant density, and this additional energy drives further expansion. It's a kind of self-reinforcing process that, if dark energy truly is constant, will continue forever, leading to exponential expansion in the far future. Currently, dark energy makes up about 68% of the total energy density of the universe. Dark matter, the invisible matter we detect through its gravitational effects, comprises about 27%. Ordinary matter, everything we can see and touch, all the stars and planets and gas and dust, amounts to just 5%. We live in a universe dominated by components we don't fully understand, with dark energy being the most dominant of all. Now, how does dark energy fit into the black hole universe hypothesis? Quite naturally, actually. A cosmological constant can exist inside a black hole just as easily as in a standalone universe. It's a property of space-time itself, not something that requires particular boundary conditions. If our universe is a black hole interior, the dark energy we observe could simply be the cosmological constant of that interior geometry. In fact, the presence of dark energy might help explain certain features of a black hole universe. The accelerated expansion it drives creates what's called a cosmological event horizon around any observer. This is a boundary beyond which galaxies are receding faster than light can travel, meaning we can never see them or communicate with them. This cosmological horizon is distinct from a black hole event horizon, but both create causal boundaries, regions beyond which information cannot reach us. If we're inside a black hole, we have two horizons to consider. The event horizon of the black hole itself, somewhere far beyond our observable region, and the cosmological horizon created by dark energy, which lies at about 16 billion light-years from us currently and will remain at roughly that distance as space expands. These two horizons coexist, each affecting different aspects of the cosmic structure. The cosmological horizon might actually help hide the black hole event horizon from our observations. Since we cannot see beyond the cosmological horizon anyway, and the black hole horizon is presumably much farther away given the enormous size required to contain our universe, we wouldn't detect the black hole boundary directly. The dark energy, by creating its own horizon, provides a natural screen beyond which we cannot observe regardless of what lies there. But dark energy also raises questions about the ultimate fate of a black hole universe. In a standalone universe with a cosmological constant, expansion accelerates forever, leading eventually to a state where each galaxy is alone in its observable universe. All matter diluted to near nothingness, all stars burned out, all black holes evaporated, leaving only cold, empty space expanding eternally. This is the heat death scenario. a future of maximum entropy and minimum useful energy. Inside a black hole, however, there's a singularity in the future, an ultimate end to space-time itself. How do these two futures reconcile? Does dark energy prevent the singularity, allowing the interior to expand forever? Or does the singularity eventually overcome the acceleration? The answer depends on details of the black hole's structure and the nature of the singularity. In some models, the dark energy drives expansion that approaches the singularity asymptotically, never quite reaching it in finite time but getting arbitrarily close. In others, the singularity is unavoidable, and dark energy merely affects how we approach it. The mathematics allows various scenarios, and without a complete theory of quantum gravity to resolve what happens at singularities, we can't say definitively which future awaits. What we can say is that dark energy is compatible with being inside a black hole. Its existence doesn't rule out the hypothesis. In some ways, it might even support it by providing mechanisms that help reconcile interior expansion with exterior observations. The dark energy could be a natural feature of large black hole interiors, perhaps even a necessary component for creating a universe-like environment within. As we contemplate this, let's appreciate the strangeness of dark energy itself, regardless of where we are. It's energy with no clear origin, no particles associated with it, no mechanism we fully understand. It simply exists, making up most of the universe's energy, driving cosmic evolution in ways we're only beginning to grasp. Whether we're in a black hole or not, dark energy remains one of the deepest mysteries in physics. And that mystery connects to our larger question in beautiful ways. We're asking whether we might be in a black hole, a structure we don't fully understand, driven partly by dark energy, which we also don't fully understand. The question brings together multiple frontiers of physics, multiple areas where our knowledge reaches its limits. Perhaps that's appropriate. Perhaps the biggest questions require connecting all our uncertainties. We've spoken of singularities several times, those points where classical general relativity predicts infinite curvature and density, where the mathematics breaks down and physics as we know it ceases to apply. If we're inside a black hole, understanding what singularities actually are becomes crucial, because one lies in our future. Let's explore what we know and what we don't about these mysterious features of space-time. In the Schwarzschild black hole, the singularity sits at the centre, at r equals 0 in the coordinates usually used. Everything inside the event horizon inevitably reaches this point, not because of any force pulling things inward, but because all time-like paths, all possible futures, lead there. It's as unavoidable as tomorrow. But what actually happens at the singularity? The equations say density becomes infinite, curvature becomes infinite, and the geometry becomes undefined. This is clearly unphysical. Nature doesn't do infinities in reality. For rotating black holes, described by the Kerr solution found by Roy Kerr in 1963, the structure is different. The singularity is not a point but a ring, and the global geometry is more complex, with multiple horizons and regions that allow, mathematically at least, for unusual causal structures. But the singularity is still there, still a place where the classical theory fails, still demanding explanation from a deeper theory. Most physicists believe that quantum gravity will resolve singularities, just as quantum mechanics prevents electrons from spiraling into atomic nuclei, which classical physics would predict. Quantum gravitational effects should prevent the formation of true singularities. At scales approaching the Planck length, about 10 to the minus 35 meters, quantum fluctuations in space-time itself should become important, perhaps creating a kind of granularity or foam structure that prevents infinite compression. Several approaches to quantum gravity suggest what might replace singularities. Loop quantum gravity, which treats space-time as woven from discrete loops, predicts a quantum bounce where matter reaches extremely high density but then rebounds, avoiding the singularity. String theory, which describes fundamental entities as vibrating strings rather than point particles, might smear out the singularity into an extended object. Other approaches suggest different resolutions, but most agree that something prevents the infinite densities classical relativity predicts. If we're in a black hole universe, the singularity in our future might not be a point of ultimate destruction, but a transition to something else. Perhaps it's a region of extremely high density but finite, where new physics takes over. Perhaps it's a boundary where our universe connects to something beyond, another space or another time. Perhaps it's the moment when the black hole completes its formation as seen from outside, though experienced from inside as billions of years of history. The timing of this singularity is important to consider. For a black hole massive enough to contain our universe, the time from formation to singularity would be related to the black hole's size and properties. The larger the black hole, generally, the longer this time. For a black hole with mass comparable to the observable universe, the interior lifetime could be hundreds of billions of years or more. We're currently about 13.8 billion years into cosmic history, so we might be in the early or middle stages of the black hole's interior evolution. We wouldn't notice the approaching singularity until relatively late in cosmic history. Space could continue expanding, dark energy could continue driving acceleration, galaxies could continue evolving, all while the singularity waits in the far future. Only when we get closer, when the geometry starts changing in measurable ways, would we detect anything unusual. And by then, it might be too late to do anything about it, if indeed there's anything that could be done. There's a particular type of singularity called a big crunch, where the universe stops expanding and starts contracting, with all matter eventually compressing back to infinite density. This is the time reverse of the Big Bang. Some cosmological models predict this if the universe's density is high enough to overcome expansion. If we're in a black hole, the singularity might resemble a big crunch, where the interior finally collapses to meet the exterior in some quantum gravitational event that transcends our current understanding. But there are other possibilities. The singularity might be space-like, meaning it occurs everywhere in space at some future time, like the reverse of the Big Bang singularity in standard cosmology. Or it might be more complex, with different regions reaching the singularity at different times in ways that depend on the black hole's internal structure. General relativity allows various scenarios, and without observations of real black hole interiors, we can't say which nature implements. What's philosophically interesting is that singularities represent boundaries of predictability. Beyond them, the laws of physics as we currently understand them don't apply. They're regions where cause and effect might break down, where the deterministic evolution of space-time ceases. If we're heading towards such a boundary, it means there's a fundamental limit to how far into the future we can predict, regardless of how well we understand current conditions. This limit applies whether we're in a black hole or not. Even in standard cosmology, we face questions about the ultimate fate of the universe that push our theories to their limits. Will the universe expand forever, eventually becoming too cold and diffuse to support any structure? Will quantum tunneling create bubble universes with different physics? Will some unknown process radically change cosmic evolution? We can extrapolate current trends, but we cannot be certain. The singularity in a black hole interior is just another version of this fundamental uncertainty about the deep future. It's a reminder that physics, for all its power, operates within boundaries, that our ability to predict and understand has limits set by the structure of space-time itself. And perhaps that's okay. Perhaps knowing that there are boundaries to knowledge is itself a kind of knowledge, a wisdom about the limits of wisdom. As we move forward from this discussion of singularities, let's carry with us this appreciation for boundaries and limits. The question of whether we're in a black hole is partly a question about what lies beyond our observational boundaries, what exists at the limits of our cosmic horizons. It's fitting that answering it requires us to grapple with singularities, those ultimate boundaries in space-time itself. Now we arrive at perhaps the most practical question in this entire exploration. Could we actually determine whether we're inside a black hole? Are there observations we could make, experiments we could perform, that would reveal our cosmic containment or rule it out definitively? The answer is subtle and depends on understanding what kinds of signatures a black hole universe might leave in observable data. Let's start with what wouldn't work. We cannot simply look for the event horizon. If we're inside a black hole massive enough to contain our universe, the horizon is far beyond anything we can observe, likely hundreds of billions or trillions of light years away. The observable universe extends about 46 billion light years in any direction, determined by how far light has travelled since the Big Bang. Anything beyond that is causally disconnected from us. We cannot receive signals from it. If the event horizon lies beyond our observable region, we have no direct way to detect it. Light from the horizon cannot reach us, and we cannot send probes to investigate it. From our perspective, the horizon might as well not exist. It affects the global structure of space-time but produces no local effects we could measure with current or foreseeable technology. What about the singularity? If one lies in our future, could we detect signs of approaching it? This is more promising but still challenging. The singularity would only become detectable when it's relatively near in cosmic time, when the geometry starts changing noticeably. This might manifest as deviations from the expected expansion history, unusual behaviour in the cosmic microwave background, or shifts in how gravitational waves propagate through space. But these effects would likely appear only billions of years before the singularity, if at all. So direct detection seems impossible with current methods, but there are indirect approaches worth considering. One involves looking for statistical signatures in the distribution of matter and energy. If our universe formed as a black hole interior, the initial conditions might differ slightly from what standard inflationary cosmology predicts. These differences could leave imprints in the cosmic microwave background or in how galaxies cluster on the larger scales. Specifically, the quantum fluctuations that seeded galaxy formation might have different statistical properties if they arose in a black hole formation process, rather than during cosmic inflation. The differences would be subtle, buried in the statistical noise of our measurements, but they might be detectable with sufficiently precise observations. Current data shows no clear deviation from inflationary predictions. But our precision is limited. Future missions measuring the cosmic microwave background with greater accuracy might reveal anomalies. Another possibility involves studying the topology of space, its global shape and connectivity. If the universe is finite, if space closes back on itself or has boundaries, that would be consistent with being inside a black hole. Infinite space would rule out the hypothesis. Since black holes have finite interiors, we can search for topological signatures by looking for repeated patterns in the cosmic microwave background, or by seeing if we can detect multiple images of the same structures in different directions. So far, such searches have found nothing. Space appears flat and possibly infinite, at least much larger than our observable region. But absence of evidence isn't evidence of absence. If the universe is finite but much larger than what we can see, we wouldn't detect the topology yet. Only if it's finite and comparable to our observable size would we have a chance of measuring it. Gravitational waves offer another avenue for investigation. These ripples in space-time, detected for the first time in 2015, carry information about the structure of space itself. In principle, gravitational waves could reveal properties of the global geometry that light cannot. If we're in a black hole, waves propagating through the interior might behave differently than in unbounded space, perhaps showing echoes or unusual dispersion patterns. Current gravitational wave detectors are not sensitive enough to see such effects, and the differences might be too small to measure even with next-generation instruments. But as the field develops, as we build space-based detectors and improve our analysis techniques, subtle geometric effects might become accessible. This is a long-term possibility, not an immediate test, but it represents a genuine observational path forward. There's also the question of whether the laws of physics themselves might differ slightly if we're in a black hole. Perhaps the fundamental constants, things like the speed of light or the strength of gravity, would vary in ways that betray our containment. However, there's no theoretical reason to expect such variations. And observations show that these constants are indeed constant across cosmic history and distance as far as we can measure. Perhaps the most promising approach is simply to keep refining our cosmological models and measurements. As we map the universe in greater detail, as we measure its expansion history more precisely, as we probe the cosmic microwave background with ever-increasing accuracy, we constrain the possibilities. Each new data point narrows the range of viable theories. Eventually, we might accumulate enough evidence to favour one scenario over others, even if we can't prove it absolutely. But there's a philosophical point worth making here. Some questions might be fundamentally unanswerable from inside the system being questioned. If we're in a black hole, we're part of that black hole's interior. We have access only to information within our light cone, our observable region. The global structure, the exterior universe, the event horizon itself, all lie beyond what we can ever observe. Our knowledge might be fundamentally limited by our position. This isn't cause for despair, but rather for humility. Science works by testing theories against observations, by comparing predictions to data. When observations are impossible in principle, we enter the realm of metaphysics, of untestable hypotheses. The question of whether we're in a black hole might have components that are genuinely scientific, testable through observation, and components that remain forever beyond empirical verification. Recognizing this boundary is part of doing science carefully. We push observations as far as possible. We develop theories that make predictions. We test what we can test. But we also acknowledge when we've reached the limits of what observation can tell us. When we're asking questions that might not have empirical answers. This acknowledgement doesn't mean we stop asking, but it means we hold our conclusions lightly with appropriate uncertainty. Let's look more carefully at one of our most important observational windows into the early universe, the cosmic microwave background radiation. This faint glow, discovered accidentally in 1965 by Arno Penzias and Robert Wilson, provides a snapshot of the universe when it was just 380,000 years old. Understanding what it tells us, and what it might reveal about our possible containment, requires exploring its properties in detail. The cosmic microwave background formed when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this recombination, the universe was a hot plasma, where photons scattered constantly off free electrons, making space opaque. After recombination, photons could travel freely, and the universe became transparent. The light we see in the cosmic microwave background has been travelling toward us ever since. Redshifted by the expansion of space from visible light to microwaves, what makes this radiation so valuable is its uniformity. The temperature is the same in all directions to about 1 part in 100,000, indicating that the early universe was extraordinarily smooth. But there are tiny fluctuations in this uniformity, hot and cold spots that vary by about 100 millionths of a degree. These fluctuations are the seeds from which all structure grew. Regions that were slightly denser than average and eventually collapsed under gravity to form galaxies and galaxy clusters. The pattern of these fluctuations encodes information about the universe's properties when the radiation was emitted. The size of the hot and cold spots tells us about the geometry of space. The amplitude of the fluctuations reveals the density of matter. The detailed statistical properties connect to the physics of the very early universe, potentially even to processes occurring fractions of a second after the Big Bang. When we analyse the cosmic microwave background carefully using satellites like COBE, Dudumap and Planck, we can measure the universe's properties with remarkable precision. We determine that space is flat or very nearly so. We measure the density of ordinary matter, dark matter. and dark energy. We constrain the expansion rate and the age of the universe. All of these measurements fit together into a consistent cosmological model that matches independent observations from galaxy surveys and supernova studies. Now, if we're inside a black hole, would the cosmic microwave background look different? This is a crucial question, and the answer is not necessarily. A black hole interior with the right properties would produce a cosmic microwave background essentially identical to what we observe. The recombination process doesn't depend on whether the universe is contained by an event horizon far beyond our observable region. The physics of atom formation, photon decoupling and subsequent evolution proceeds the same way. However, there might be subtle signatures if we know where to look. The initial quantum fluctuations that grew into the temperature variations we see could have different statistical properties depending on how they were generated. In the standard inflationary model, these fluctuations arose from quantum jitters in the inflaton field, the hypothetical field that drove cosmic inflation. In a black hole formation scenario, they might arise differently, perhaps from quantum fluctuations in the collapsing matter that formed the black hole. These different origins might produce different patterns in the fluctuations. Inflation predicts an almost perfectly scale-invariant spectrum, meaning fluctuations of all sizes have similar strength. It also predicts negligible non-Gaussianity, meaning the fluctuations follow Gaussian statistics. Any deviation from these predictions might hint at alternative physics in the very early universe, potentially including black hole formation. Current measurements show the cosmic microwave background is indeed nearly scale-invariant and Gaussian, consistent with inflation. But there are hints of anomalies, features that don't quite fit the simplest inflationary models. There's a slight hemispherical asymmetry, where one half of the sky shows slightly larger fluctuations than the other. There's a deficit of power on the largest angular scales, fewer big fluctuations than expected. These anomalies are statistically marginal, possibly just flukes of our particular observable region, but they've persisted across multiple satellite missions. Could these anomalies hint at a black hole origin? It's possible, but far from certain. Many explanations exist for such features, including more complex inflationary models, interactions between the inflaton and other fields, or even contamination from foreground sources we haven't fully removed. The black hole hypothesis is one possibility among many, not clearly favoured by current data. There's something profound about using light from the early universe to probe our possible containment. The cosmic microwave background photons have been travelling for 13.8 billion years, crossing nearly the entire observable universe to reach us. They carry information from close to the beginning of cosmic time, from conditions far removed from what we experience today. Yet they tell a story consistent with either a standalone universe or a black hole interior of sufficient size. This consistency is actually important. It means the black hole hypothesis isn't invented to explain anomalies in data. It's not a desperate attempt to resolve inconsistencies. Rather, it's an alternative interpretation of observations that fit the standard model well. The data doesn't demand a black hole interpretation, but it allows one. And that's a different kind of suggestion, one based on possibility rather than necessity. As we study the cosmic microwave background in ever greater detail, we're mapping the early universe with increasing precision, constraining models, testing theories, pushing toward better understanding. Whether this eventually reveals that we're in a black hole or confirms the standard cosmology, the process itself is valuable. We're learning about our cosmic origins, about the physics of extreme conditions, about the structure of space-time itself. The answer matters, but so does the careful exploration required to find it. Shifting our attention now from the early universe to its current structure, let's explore how galaxies are distributed through space and what this might tell us about our possible containment. The universe is not uniform today. Matter clusters into galaxies. Galaxies gather into groups and clusters, and these clusters connect into filaments and walls surrounding vast voids. This cosmic web of structure formed over billions of years from tiny initial density variations, growing through gravitational collapse into the complex patterns we observe. Understanding this structure requires starting with gravity, the force that drives cosmic architecture. In regions where density was slightly higher than average, gravity pulled in more matter, increasing the density further. This created a runaway process where dense regions got denser and empty regions got emptier. Over time, small fluctuations grew into galaxies, then into larger structures. Following patterns determined by gravity, dark matter, and the expansion of space. The distribution of galaxies today reflects both the initial conditions set in the very early universe and the subsequent evolution through billions of years. When we map galaxies across large volumes of space, we see filamentary structures, long chains of galaxies connecting clusters. These filaments surround voids, regions where galaxy density is much lower than average. The overall pattern resembles a cosmic foam or sponge, with matter concentrated along surfaces and filaments while most of volume remains relatively empty. This web-like structure is beautifully explained by standard cosmology, computer simulations starting from initial conditions consistent with the cosmic microwave background and evolving matter under gravity and dark matter interactions, reproduce the observed structure remarkably well. We can watch galaxies form in these simulations, cluster together, merge, and create patterns that match what telescopes reveal in the real universe. Now, would this structure differ if we're inside a black hole? Again, the answer is subtle. The growth of structure depends on gravity, dark matter, and the expansion history of the universe. If a black hole interior has the same matter content and expansion history as a standalone universe, structure would grow in the same way. The cosmic web would look identical because the underlying physics driving its formation is the same. However, there might be differences on the very largest scales approaching the size of our observable universe. If space is finite, if there's a topology imposed by the black hole's containment, we might see correlations or patterns at these scales that wouldn't appear in an infinite universe. For instance, structures on opposite sides of the observable universe might show statistical connections if light or gravitational influences have propagated around the space. Current surveys mapping galaxy distributions have not found such large-scale correlations beyond what random chance would produce. The universe appears statistically homogeneous and isotropic, the same in all directions. Even on the larger scales we can measure. This is consistent with either infinite space or finite space much larger than our observable region. The black hole hypothesis is allowed but not required by the data. There's another consideration involving dark matter. This invisible matter, detected only through its gravitational effects, makes up about 85% of all matter in the universe. It doesn't interact with light, doesn't emit or absorb radiation, and reveals itself only by affecting how galaxies move and how light bends around massive structures. Dark matter forms a scaffolding on which galaxies form, providing the gravitational wells that attract ordinary matter. As we continue mapping the universe, as we catalogue more galaxies and measure their properties in greater detail, we refine our understanding of structure formation. We test our theories against observations, we discover new phenomena like dark energy's effects on structure growth, and we push toward more complete pictures of cosmic evolution. This work stands on its own, valuable for understanding how the universe developed, independent of questions about containment. But it also provides data relevant to our larger question, helping constrain what scenarios remain viable. One of the most fascinating aspects of being inside a black hole, if indeed we are, involves how time would work differently for us compared to observers outside. General relativity predicts that time runs at different rates in different gravitational fields, a phenomenon called gravitational time dilation. Understanding this effect, and what it might mean for our cosmic history requires thinking carefully about how time itself is relative. The basic principle is straightforward. Clocks in stronger gravitational fields run slower compared to clocks in weaker fields. This isn't an illusion or measurement error. Time genuinely passes at different rates. An observer deep in a gravitational well ages more slowly than someone far from massive objects. This has been verified experimentally countless times, from atomic clocks flown on aircraft to satellite navigation systems that must account for relativistic effects to maintain accuracy. Near a black hole's event horizon, time dilation becomes extreme. From the perspective of someone watching from far away, objects falling toward the horizon appear to slow down asymptotically, taking infinite time to actually cross. Light from the falling object redshifts, becoming dimmer and more stretched in wavelength until it fades from view. The falling object seems frozen at the horizon, though from its own perspective it crosses in finite time and continues inward. Now, if our entire universe is inside a black hole, we're all in the same gravitational field, all experiencing the same time dilation relative to the exterior. Within our universe, our clocks run at the same rate as each other. We measure time in years, we see events unfold in sequence, we age and evolve at normal rates. But compared to the exterior universe, if one exists, our time might run very differently. Consider what this means for cosmic history. From our perspective inside the black hole, 13.8 billion years have passed since the Big Bang. We've evolved through various epochs: the radiation-dominated era, the matter-dominated era, the current dark energy-dominated era. Galaxies have formed, stars have lived and died, complex structures have emerged. This is our history, measured in our time. But from the perspective of the exterior universe, the parent space in which our black hole exists, less time might have passed. If time dilation is significant, the entire history of our universe, from formation to eventual end, might occur in a much shorter period as measured outside. The exact ratio depends on details of the black hole's formation and our position within the interior, but the effect could be substantial. There's something philosophically interesting about this. Time is not a universal background ticking uniformly everywhere. It's a local property, something that depends on where and how you're measuring it. This locality is fundamental to relativity, but it has profound implications. It means that asking _quote_3_ doesn't have a single answer, independent of where you're asking from. Age, duration, and simultaneity are all relative concepts. If we're in a black hole, our universe's age of 13.8 billion years is correct from our perspective, but might not match external measures. Both are valid. Both describe genuine physical time. The difference isn't about which is right, but about understanding that time itself varies. This relativistic view of time is one of Einstein's greatest insights, and it applies directly to our question about cosmic containment. As we think about cosmic evolution, about the history of the universe from Big Bang to present, we should remember that this history is measured in our time, experienced at our rate. Whether faster or slower than some external clock, it's the real timeline of our experience. The time dilation doesn't make our history less real or our measurements less valid. It simply places our cosmic story in a larger context where time itself is part of the dynamic structure being described. As we reach the midpoint of our exploration, let's step back from the mathematics and observations to consider what it would actually mean if we discovered we're inside a black hole. How would this knowledge affect our understanding of existence, our place in the cosmos, our sense of meaning and purpose? These are not scientific questions in the narrow sense, but they matter deeply for how we integrate such a discovery into our worldview. First, there's the question of boundaries. We tend to think of the universe as everything that exists, the totality of reality. If we're in a black hole, that changes. The universe becomes a subset of something larger, contained within a structure that exists in a parent space. There would be realms beyond our event horizon, regions we can never observe or access, but which are nonetheless real. Our universe would be local, finite, bounded, rather than universal in the absolute sense. This wouldn't make us less significant, but it would change the framework of significance. Instead of being inhabitants of all there is, we'd be inhabitants of a particular region of a larger reality. It's similar to how the Copernican revolution showed that Earth isn't the centre of the universe, or how discovering other galaxies revealed the Milky Way is just one among billions. Each expansion of perspective initially felt diminishing, but ultimately enriched our understanding. Being in a black hole would be the next step in this series of cosmic demotions. Not the centre of the universe, not in a unique galaxy, not even in a unique universe, but inside a structure within a larger space. Yet this need not be depressing. It could be liberating. Opening possibilities we haven't considered. If black holes can contain universes, perhaps there are countless other universes in other black holes, each with its own physics, its own history, its own opportunity for structure and complexity. There's also the question of creation and origin. 90 minutes. You've been here for 90 minutes, quietly, patiently, choosing this over everything else the world was offering you tonight. Do you know how rare that is? Most people cannot sit with something slow and meaningful for more than a few minutes before reaching for something louder. But not you. Not tonight. This channel exists for exactly this kind of person, and a like and subscribe is how we find more of them. It is how we find each other. Thank you for still being here. Now let's continue. There's also the question of creation and origins. If our universe is a black hole interior, it had a definite beginning, the moment the black hole formed. But that moment might not be fundamental. It might be a transition from a previous state in the parent universe. Matter collapsing beyond a point of no return. Our Big Bang would be a local event, significant to us, but not cosmically unique. Possibly one of many such events occurring in the larger space. This shifts the ultimate question slightly. Instead of asking, quote, 4, we might ask, quote, 5. Instead of wondering about the origin of everything, we might wonder about the processes that lead to our particular kind of existence. The mystery doesn't disappear, but it relocates, becoming a question about mechanisms rather than absolute beginnings. Philosophically, the black hole universe idea connects to old questions about the nature of reality and our access to it. If there are regions beyond our observational horizon, parts of reality we can never see or interact with, what does that mean for knowledge? Are they real in the same sense as what we can observe? This is related to debates about scientific realism, about whether science discovers reality or merely constructs models that work for our observable domain. One stance, called empiricism, says that only what we can observe has scientific meaning. From this view, regions beyond the event horizon might exist mathematically, but don't matter for science because they are unobservable. Another stance, called realism, says that science aims to describe reality as it is, independent of our observations. From this view, the parent universe and exterior space are as real as our interior, even if we can't access them. I lean toward realism, toward thinking that reality extends beyond what we can observe, but I acknowledge the limits this places on certain knowledge claims. We can theorize about exteriors, we can use mathematics to describe what might lie beyond our horizons, but we can't verify these theories empirically in the usual sense. We're reasoning about the structure of the unobservable, which requires different standards of evidence. Ultimately, discovering we're in a black hole would be a profound expansion of perspective. It would answer some questions while raising new ones. It would connect our universe to larger structures while emphasizing our unique position within this particular interior. It would give us definite boundaries and a finite lifetime while opening possibilities about what else might exist. Most of all, it would remind us that reality is larger and stranger than we typically imagine, that our cosmic story is one chapter in a vaster narrative we're only beginning to comprehend. Before going further with the black hole hypothesis, we should examine the standard cosmological model carefully, understanding what it explains and why it's so widely accepted. The lambda CDM model, our best current description of cosmic evolution, has proven remarkably successful at predicting and explaining observations across vast ranges of scale and time. Appreciating its strengths helps us evaluate whether alternatives like the black hole universe are necessary or merely possible. The standard model begins with the Big Bang, a state of extremely high density and temperature that occurred about 13.8 billion years ago. Not an explosion in space, but an explosion of space itself, an expansion that began from conditions we can barely describe and has continued ever since. In the earliest moments, the universe was far too hot for atoms to exist. Even protons and neutrons couldn't form. Only fundamental particles and radiation filled space. As expansion cooled the universe, particles could combine. In the first few minutes, protons and neutrons fused into light elements, primarily hydrogen and helium with traces of lithium. This nucleosynthesis period left specific ratios of elements that we can calculate precisely and measure in ancient gas clouds. The observed ratios match predictions beautifully. One of the Big Bang model's great successes. After 380,000 years, as we've discussed, electrons and nuclei combined into atoms, allowing light to travel freely. The cosmic microwave background preserves this moment. Over the following hundreds of millions of years, gravity amplified density fluctuations, creating the first stars and galaxies. Structure grew hierarchically, small objects forming first and merging into larger ones. This process continues today as galaxies cluster and collide. The model includes dark matter, necessary to explain galaxy rotation curves, gravitational lensing, and structure formation rates. It includes dark energy, necessary to explain accelerated expansion observed over the past few billion years. These mysterious components make up 95% of the universe's energy content. Yet the model describes their effects with just a few parameters. The simplicity is elegant, even while the nature of these components remains unknown. Lambda CDM makes specific predictions that can be tested. It predicts how the expansion rate should change over cosmic history. It predicts the statistical properties of cosmic microwave background fluctuations. It predicts how structure should grow at different times. It predicts the abundances of light elements. Observations confirm these predictions again and again from multiple independent lines of evidence. This concordance is remarkable. We measure the universe's age from stellar evolution, from radioactive dating, from expansion rate calculations, and get consistent answers around 13.8 billion years. We measure the density of matter from galaxy clustering, gravitational lensing, and cosmic microwave background, and get consistent values. We measure the expansion rate from supernova, from standard rulers and galaxy distributions, from the cosmic microwave background. And while there's currently a small tension between some methods, they broadly agree. The model also explains why the night sky is dark, Olber's paradox. In an infinite, eternal, static universe, every line of sight would eventually hit a star, making the sky bright. But in an expanding universe with a finite age, only light from a finite region has reached us, and that light is red-shifted and diluted by expansion. The darkness of night is evidence for the Big Bang. It explains the cosmic microwave background's existence and temperature. It explains why distant galaxies are younger when we observe them. It explains the large-scale structure of the universe. It connects observations from different eras and scales into one coherent picture. This coherence is what makes scientists confident the model is fundamentally correct, even while details remain uncertain. What the standard model doesn't fully explain are certain foundational questions. Why did the Big Bang happen? What, if anything, came before? Why do the fundamental constants have the values they do? Why is there something rather than nothing? These questions lie at the boundaries of science, touching on philosophy and perhaps requiring physics beyond current theories. The black hole hypothesis potentially addresses some of them by embedding our universe in a larger structure. But it doesn't eliminate the questions entirely, it just moves them. If our universe is a black hole interior, we still need to explain the parent universe. Where did it come from? What are its properties? Why does it produce black holes that create universe-like interiors? We've shifted the mystery but not resolved it. This is common in cosmology. Each answer raises new questions. Each explanation requires deeper explanations. Perhaps there's no final answer, no ultimate foundation, only an endless chain of context within contexts. Or perhaps there is something fundamental we haven't discovered yet, some principle or structure that makes sense of everything, including why universes exist in black holes. We can't know without further investigation, without pushing our theories and observations to new limits. The Standard Model is our current best understanding. The black hole hypothesis is a possibility worth exploring. Both contribute to the larger project of comprehending cosmic reality. Let's examine one of the most important additions to the standard Big Bang model. Cosmic inflation, the hypothesis that the universe underwent a period of extraordinarily rapid expansion in its first tiny fraction of a second. Inflation was proposed to solve several puzzles in cosmology, and it's become the leading framework for understanding the very early universe. But how does it relate to the question of whether we're in a black hole? The puzzles inflation addresses are genuine mysteries in standard Big Bang cosmology. First is the horizon problem. The cosmic microwave background shows the universe was uniform in temperature to about 1 part in 100,000 at 380,000 years old. But regions we observe on opposite sides of the sky were never in causal contact in standard Big Bang evolution. Light hadn't had time to travel between them, so how did they know to be the same temperature? Second is the flatness problem. For space to be as flat as we observe today, the early universe's density must have been extraordinarily close to the critical value, accurate to many decimal places. Any slight deviation would have grown rapidly, leading to obvious curvature now. This fine-tuning seems implausible without some mechanism setting the initial conditions precisely. Third is the monopole problem. Certain grand unified theories predict that topological defects like magnetic monopoles should form in the early universe in large numbers. We should see these exotic particles, but we don't. Their absence requires explanation. Inflation solves all three puzzles elegantly. It proposes that between about 10 to the minus 36 and 10 to the minus 32 seconds after the Big Bang, the universe expanded exponentially, growing by a factor of at least 10 to the 26, possibly much more. This expansion was driven by a special field called the inflaton, which had a nearly constant energy density during the inflationary period, behaving like a cosmological constant. This rapid expansion stretched any initial curvature to negligible levels, like inflating a balloon until its surface appears flat. It took a small region that was in causal contact and blew it up to encompass the entire observable universe, and far beyond. Everything we see today came from a tiny patch that had time to reach uniform temperature before inflation began, and it diluted any monopoles or other defects to undetectable densities. Inflation also provides a mechanism for generating the density fluctuations that seeded structure formation. Quantum fluctuations in the inflaton field, tiny variations at microscopic scales, got stretched to cosmic sizes by the exponential expansion. When inflation ended and the inflaton decayed into ordinary matter and radiation, these fluctuations became density variations in the primordial plasma. Gravity then amplified them over billions of years into galaxies and large-scale structure. One testable difference might involve primordial gravitational waves. Inflation predicts that quantum fluctuations in space-time itself, not just in matter fields, got amplified to cosmic scales. These gravitational wave perturbations should leave a specific signature in the polarization of the cosmic microwave background. Detecting this signature would confirm inflation and provide information about the energy scale at which it occurred. If our universe is a black hole interior, the gravitational wave signature might differ slightly from standard inflation predictions, depending on how the black hole formation and interior inflation connect. This is speculative, but it represents the kind of observation that might eventually distinguish between scenarios. As we improve our measurements of the cosmic microwave background polarization, we narrow the possibilities. For now, inflation remains our best explanation for very early universe conditions, solving multiple problems with one mechanism. Whether it occurred in a standalone universe or inside a black hole, the physics of inflation would work the same way, producing the same observable consequences. The question of containment is orthogonal to the question of inflation. Both might be true, neither might be true, or one without the other. They address different aspects of cosmic structure. The idea that our universe might be inside a black hole naturally connects to broader concepts of multiverses, the hypothesis that our universe is one among many. Let's explore various multiverse proposals, understanding how they relate to each other and to our central question. These ideas push the boundaries of science, touching on what can be known and what must remain speculative. The simplest multiverse concept is the infinite space multiverse. If space extends infinitely, and the universe has the same average properties everywhere, then by pure statistics, every possible arrangement of matter must occur somewhere, far beyond our observable region. There would be other regions where matter happened to arrange itself exactly like here, forming identical copies of Earth, of you, of this moment. This follows from probability in infinite space. This multiverse isn't really multiple universes, but rather one infinite universe with infinite variation. It's a consequence of spatial infinity plus random initial conditions, not requiring exotic physics. However, it's untestable. We cannot observe these distant regions, cannot verify their existence, cannot communicate with them. They exist as mathematical consequences of assumptions, not as directly observed realities. A second type is the quantum multiverse, arising from certain interpretations of quantum mechanics. In the many worlds interpretation, every quantum measurement causes the universe to split into multiple branches, one for each possible outcome. All possibilities actually occur, just in different parallel universes. These universes are not separate spaces but different branches of the same quantum wave function, each experiencing a different history. This quantum multiverse is controversial. Many physicists reject the many worlds interpretation, preferring other ways of understanding quantum mechanics that don't require infinite universe splitting. The interpretation doesn't make different predictions than alternatives for any observable phenomena, so it's a matter of philosophical preference which interpretation to adopt. The quantum multiverse is real if many worlds is correct, but that if remains disputed. A third type is the inflationary multiverse we mentioned earlier. If inflation is eternal, creating infinite bubble universes, each bubble is effectively a separate universe with potentially different properties. The inflaton field might settle to different values in different bubbles, leading to different physics, different particles, different constants of nature. Our universe would be one bubble among infinitely many. This multiverse is somewhat more testable than others. If eternal inflation is correct, there might be observable signatures, such as collisions between bubble universes that could leave imprints in our cosmic microwave background. No such signatures have been found yet, but the possibility exists. This makes the inflationary multiverse a scientific hypothesis rather than pure speculation, though still highly speculative. A fourth type is the landscape multiverse from string theory. String theory, which attempts to unify quantum mechanics and gravity by treating particles as tiny vibrating strings, suggests there might be something like 10 to the 500 different possible vacuum states, each with different physical properties. If all these states are realized somewhere in a larger space, we get a vast multiverse of universes with varying physics. The landscape multiverse connects to the inflationary multiverse if different bubble universes settle into different string theory vacua. This creates enormous diversity. Some universes might have electrons much heavier than ours, some might have stronger gravity, some might not allow atoms to form. Our universe's particular physics would be one possibility among countless others. Now, where does the black hole universe fit into this taxonomy? It's actually a different kind of multiverse proposal. Instead of parallel universes in separate spaces or quantum branches, or bubble universes scattered through an inflating space, the black hole multiverse is hierarchical. Universes exist inside black holes, which exist in parent universes, which might themselves be inside larger black holes, potentially without end in either direction. This hierarchy could combine with other multiverse types. For instance, if eternal inflation is true, and black holes in each bubble universe spawn new universes, you'd have both a horizontal multiverse of bubble universes and a vertical multiverse of nested black hole universes. The structure would be immensely complex, with universes inside universes, beside universes, beside universes, all embedded in an eternally inflating space. Or consider quantum many-worlds combined with black hole universes. Every quantum event splits the universe, and in some branches, black holes form that spawn child universes, which themselves split quantum mechanically, creating an exponentially branching tree of universes at every level. The complexity becomes almost impossible to visualize, though the mathematics might be well defined. Whether any particular multiverse theory is true remains unknown. We have intriguing theoretical frameworks, suggestive mathematics, and connections to well-tested physics. But we lack direct evidence, observations that would confirm these vast structures beyond our horizon. As with the black hole universe hypothesis specifically, we're reasoning about the unobservable, guided by theory but unable to verify conclusively. As we continue exploring possibilities, we should consider how quantum gravity theories might change our understanding of black holes and whether we could be inside one. General relativity, our current best theory of gravity and space-time, is classical, meaning it doesn't incorporate quantum mechanics. But at extreme energies and densities, quantum effects should become important. Several approaches to quantum gravity have been developed, each offering different perspectives on black holes. String theory, which we've mentioned, treats particles as one-dimensional strings vibrating in higher dimensional space. Instead of point-like particles creating singularities where mathematics breaks down, strings are extended objects that smear out the mass. In string theory, black holes are complex objects with internal structure, possibly resolving singularities into something finite and describable. String theory also predicts that space-time has more than 4 dimensions. With the extra dimensions curled up at tiny scales we haven't detected, black holes in string theory involve all these dimensions, and their properties depend on the geometry of the compact dimensions. This gives black holes a vast number of possible internal states, which helps explain their entropy, the amount of information they can contain. For our question, string theory might allow black hole interiors to have different properties than general relativity predicts. The singularity might be replaced by a string scale structure, a kind of quantum geometry that avoids infinite curvature. The interior could evolve in ways that depend on string physics, potentially creating conditions favourable for universe-like expansion. However, string theory is still being developed, and its predictions about black hole interiors remain uncertain. Loop quantum gravity takes a different approach, treating space-time itself as quantized, built from discrete loops of area and volume at the Planck scale. In this picture, space isn't infinitely divisible. Below the Planck length, about 10 to the minus 35 meters, the very concept of continuous space breaks down. Space-time is granular, like atoms but for geometry itself. Each of these quantum gravity approaches is incomplete. None has made predictions we can test experimentally at current technology levels. The energies required to probe quantum gravitational effects, the Planck energy, are about 10 to the 19 giga-electron volts, far beyond what particle accelerators can achieve. We can't create quantum gravity conditions in the lab, so we rely on theoretical consistency and observations of extreme astrophysical environments. Black holes provide natural laboratories for quantum gravity, places where these effects should be important. But we can't observe black hole interiors directly. We can only study their exteriors, their event horizons, their effects on surrounding matter. This limits what we can learn empirically about quantum gravity from black holes, though observations of gravitational waves from merging black holes are beginning to provide new constraints. For our question about living in a black hole, quantum gravity theories offer possibilities beyond what classical general relativity allows. They suggest that interiors might be more complex, might avoid singularities, might create conditions that support expanding universes. But they don't definitively answer whether our universe is such an interior. That remains an open question that requires both better quantum gravity theories and better observations. What quantum gravity does emphasize is that our understanding of space-time is incomplete. General relativity, for all its successes, is not the final word. At extreme scales, new physics takes over, physics we're still discovering. This new physics might reveal that black hole interiors are profoundly different from what classical theory suggests, perhaps more hospitable to structure and complexity, perhaps more universe-like. There's something exciting about this frontier. We're at a point in physics where multiple deep questions intersect. What is quantum gravity? What happens at singularities? What is the structure of space-time? Can universes exist in black holes? These questions feed into each other, each advance in one area potentially unlocking others. The coming decades might bring breakthroughs that clarify these issues, or they might reveal that the questions are even deeper than we thought. Either way, the exploration continues. We build theoretical frameworks, we make observations, we test what we can test and reason carefully about what we can't. The question of whether we're in a black hole sits at this intersection of theory and observation, of known physics and uncertain extensions, of the observable and the forever hidden. It's a question that captures both the power and the limits of human knowledge. As we near the end of this act, let's reflect on the role of observation in addressing our central question. Science progresses through the interplay of theory and observation. We develop ideas about how nature works. We test them against what we can measure. We refine our ideas based on results. But what happens when we ask questions that observations might never answer? How do we navigate the boundary between science and speculation? The core challenge with the black hole universe hypothesis is that many of its distinctive features involve regions we cannot observe. The event horizon, if it exists, lies far beyond our cosmic horizon. The parent universe, if it exists, is causally disconnected from us. The ultimate singularity, if it exists, lies far in the future beyond our ability to predict. These are not features we can point telescopes at and study directly. This doesn't make the hypothesis unscientific, but it does change how we evaluate it. Instead of direct observation, we look for indirect evidence, for subtle signatures that might distinguish scenarios. We look for statistical anomalies in the cosmic microwave background, for unusual patterns in galaxy distributions, for deviations from expected expansion histories. These are difficult measurements, requiring extraordinary precision and careful analysis. We also rely on theoretical consistency. Does the hypothesis fit with established physics? Does it make mathematical sense? Does it resolve problems or create new ones? A theory that's consistent with known laws, that provides a coherent framework for understanding observations, deserves consideration even if some aspects remain unverifiable. This is how we think about other theoretical structures like quarks before we could isolate them, or the Earth's core before we could sample it. But there's a limit to how far theoretical consistency alone can take us. Multiple theories can be internally consistent while predicting different realities. Observation is what breaks the tie, what tells us which of several possible theories actually describes our world. Without observational discriminators, we're left with philosophical preferences, aesthetic judgments, or practical utility as guides. Or it might. Some questions could be genuinely unanswerable, not because of technological limitations, but because of fundamental constraints on what any observer inside a system can know about that system's global structure. If we're in a black hole, the event horizon might be an absolute barrier to certain knowledge. We might be able to reason about it, to develop consistent theories describing it, but never to verify those theories empirically. Learning to live with uncertainty, with questions that might not have definite answers, is part of mature science. We've done this before. Quantum mechanics leaves certain properties fundamentally uncertain. General relativity has coordinate choices that don't affect physics but appear in equations. String theory has landscape solutions we might never distinguish observationally. In each case, we've learned to work with the uncertainty, to extract what knowledge we can while acknowledging limits. The black hole universe hypothesis might belong in this category, a question we can ask, explore and reason about, but perhaps never answer definitively. And that's okay. Not every question needs a final answer for the inquiry to be valuable. The exploration itself, the careful thinking about possibilities, the development of theoretical tools to address such questions, all contribute to human understanding even if the specific question remains open. As we move into our final act, we'll think about what it means to ask questions at the boundaries of knowledge, to probe the limits of what we can know, and to find peace in uncertainty. The question of whether we're in a black hole is ultimately a question about our relationship to the cosmos, about how much of reality we can access, about whether the universe we observe is all there is or a subset of something larger. These are profound questions worthy of our careful attention, regardless of whether we can answer them completely. We've reached the contemplative phase of our journey, where we step back from the details of physics and mathematics to think about knowledge itself, about what it means to ask questions that might not have answers. This is not a retreat from science, but a deepening of it, recognizing that understanding our limits is itself a form of understanding. Throughout history, humans have encountered boundaries to knowledge. Before telescopes, we couldn't know what stars were made of. Before microscopes, we couldn't know about cells. Before relativity, we couldn't know that time is relative. Each technological and conceptual advance pushed these boundaries outward, revealing previously hidden aspects of reality. It's natural to assume this progress continues indefinitely, that eventually we'll know everything worth knowing. But there might be genuine limits, boundaries that technology cannot overcome because they're built into the structure of reality itself. The speed of light limit means we can never observe regions receding faster than light. The quantum uncertainty principle means we can never simultaneously know certain pairs of properties with arbitrary precision. These aren't technological limitations, but features of nature. This humility isn't defeatism, it's realism about the human condition. We're finite beings with limited perspectives trying to understand an enormous cosmos. We've made extraordinary progress, revealing the structure of atoms, the history of the universe, the nature of space and time. But we're still embedded in a particular place and time, with access only to our light cone, our causal patch of space-time. What lies beyond might be forever hidden, and yet we still ask. We still theorize and calculate and imagine. Even if we can never verify whether we're in a black hole, the question enriches our understanding. It pushes us to think carefully about space-time structure, about observational limits, about the relationship between local physics and global topology. It connects multiple areas of physics and philosophy. The inquiry itself has value independent of whether we reach definitive answers. This is perhaps the deepest insight about the limits of knowledge. Recognizing them is itself knowledge. Knowing what we cannot know is different from pure ignorance. It's a sophisticated understanding of the structure of reality and our place in it. We understand why certain things are hidden, what physical principles create the boundaries, what might become accessible with better theories or observations. The limits aren't arbitrary, but meaningful. As we continue through this final act, we'll explore how to find peace with such limits, how to appreciate the universe we can observe while acknowledging vast realms beyond our reach, how to hold the question of our cosmic containment with appropriate wonder and uncertainty. The goal isn't to answer every question, but to understand them deeply, to see how they connect, and to recognize both the power and the limits of human inquiry. There's a paradox in our relationship with uncertainty. We seek knowledge, we value understanding, we want definitive answers to important questions. Yet there's something beautiful, something enriching, about questions that remain open, about mysteries that persist despite our best efforts to resolve them. Let's explore this paradox, understanding what we might gain from not knowing whether we're inside a black hole. First, uncertainty keeps us humble. When we think we have reality figured out, when we're confident in our complete understanding, we risk intellectual arrogance. History shows repeatedly that such confidence is premature. Newtonian physics seemed complete until relativity. Classical mechanics seemed fundamental until quantum mechanics. Each time we thought we'd reached the final theory, nature surprised us with deeper complexity. The question of whether we're in a black hole reminds us that current knowledge might not be complete. The universe might be stranger than we imagine. There might be structures and scales beyond what we've discovered. This openness to surprise, this recognition that our maps of reality are always provisional, is essential for scientific progress. It keeps us searching, questioning, testing. Second, uncertainty creates space for wonder. When everything is explained, when every question has an answer, the universe becomes predictable, mechanical, perhaps less inspiring. But when profound mysteries remain, when we look up at the night sky and genuinely don't know if it's contained by an invisible boundary billions of light years away, there's room for awe, for imagination, for the feeling that reality exceeds our grasp. This isn't an argument for mysticism or for abandoning rational inquiry. It's recognizing that rationality itself can lead us to boundaries where wonder is the appropriate response. We wonder not because we're ignorant, but because we understand enough to see how much more there might be. Informed wonder is different from naive confusion. It's wonder that comes from comprehension of complexity. Consider how this applies personally. Each of us navigates life with incomplete information, uncertain about the future, unable to know many things we'd like to know. We make decisions, we form beliefs, we create meaning, all within this context of limited knowledge. The cosmic question of black hole containment is like a scaled-up version of this everyday condition. We're finite beings asking about infinite or at least vastly larger structures. Learning to be comfortable with cosmic uncertainty might help us be comfortable with personal uncertainty. If we can accept that some questions about the universe might never be answered, perhaps we can accept that some questions about our own lives, our purposes, our futures, also lack definite answers. Perhaps we can find peace in exploration rather than resolution, in the journey rather than the destination. There's also aesthetic beauty in open questions. A mystery is like an unfinished symphony, a painting with spaces left intentionally blank, a story whose ending remains to be written. The black hole universe hypothesis adds a particular kind of poetry to our cosmic story. We might be inside a structure so vast we can never see its boundaries, living out billions of years that might be mere moments in a large timescale, expanding while ultimately contained. This image, whether true or false, is evocative. It changes how we think about cosmic horizons, about the meaning of infinity, about our relationship to space and time. Even if we never verify it, the image has entered human thought, becoming part of how we imagine our cosmic situation. It enriches our conceptual palette, giving us new metaphors for thinking about existence. Finally, uncertainty reminds us that science is ongoing. It's not a completed edifice of facts, but a continuing process of inquiry. Each generation inherits questions from the previous one, makes what progress it can, and passes on new questions to the next. The black hole universe question might be one we pass on, perhaps with better tools for addressing it, perhaps with new theoretical insights, but possibly still open. And that's okay. The value of a question doesn't depend solely on our ability to answer it. Some questions are valuable precisely because they're hard, because they push us to our limits, because they require us to develop new capacities. The question of cosmic containment is such a question. Whether we answer it in our lifetimes, in future centuries, or never, the pursuit enriches us. As we approach the end of our journey, let's think about what it means to hold a question without demanding an answer, to carry uncertainty without it becoming a burden. The question of whether we're inside a black hole might never be definitively resolved. How do we find peace with that possibility? Part of the answer lies in changing our relationship to questions themselves. We often treat questions as problems to be solved, puzzles that must be completed. When we can't solve them, we feel frustrated, unsatisfied, as if we've failed. But some questions aren't puzzles with hidden solutions waiting to be found. They're invitations to think more deeply, to explore possibilities, to expand our conceptual frameworks. The black hole universe question is like this. Even if we never determine the truth, asking it has led us to think about space-time structure, about observational limits, about the nature of scientific knowledge. We've explored general relativity, quantum gravity, multiverse theories, the philosophy of science. We've connected ideas across disciplines, developed new perspectives on cosmic structure. The question has been generative regardless of whether we can answer it. This is true of many deep questions. Asking, what is consciousness, has driven neuroscience, philosophy of mind, artificial intelligence research, even if we don't have a complete answer. Asking, quote, 7 has inspired countless philosophical and religious traditions, scientific cosmologies, and personal reflections. Even though existence might not have a quote 8 in the causal sense we expect, the black hole universe question fits in this category of generative mysteries. It's not a question where we're simply missing data that would settle it. It's a question that might be fundamentally underdetermined by accessible observations, where multiple scenarios remain compatible with everything we can measure. And yet the exploration enriches us. The thinking shapes our understanding. The wonder it evokes is itself valuable. There's a certain kind of maturity in accepting this. It's the maturity of recognizing that reality doesn't owe us answers in the format we prefer. The universe is what it is, structured however it's structured, and our ability to know its complete nature has limits. These limits aren't failures of human endeavour, but features of the situation. We're inside the system trying to understand the system's global properties. Some aspects might always remain opaque from our perspective. Accepting this doesn't mean abandoning inquiry. We still do the science, still make the observations, still develop the theories, but we do it with appropriate humility, recognizing that some results might not be forthcoming no matter how hard we try. The goal shifts from answering every question to understanding as deeply as possible, while acknowledging boundaries. There's also comfort in recognizing that we're not alone in this situation. Every generation of scientists has faced questions beyond their ability to answer. Ancient astronomers couldn't know what stars were made of. Medieval scholars couldn't know about microorganisms. Early 20th century physicists couldn't know about quarks. Each generation did what it could with available tools, passed on unsolved questions and trusted future generations to make progress. We're in a similar position regarding cosmic structure. We've made enormous progress understanding the observable universe, mapping its contents, reconstructing its history, predicting its evolution. But global topology, ultimate origins, and structures beyond our horizons might remain mysterious for now or forever. Future generations might develop new tools, new theories, new insights that clarify these issues, or they might inherit the same uncertainties we have. Either way, we contribute what we can. We add to the accumulated knowledge. We refine the questions. We develop better frameworks for thinking about them. This contribution has value even if it doesn't produce final answers. Science is a relay race where each generation passes the baton, not a puzzle where one person must see the completed picture. There's peace in this long view. We're part of an ongoing human project that extends far beyond our individual lifetimes. The questions we care about might not be resolved while we live, but they'll remain alive for others to explore. Our thinking, our observations, our theories become part of the context in which future inquiry occurs. We're links in a chain of understanding that extends from ancient skywatchers to future cosmic explorers. The mystery of cosmic containment connects us to this larger story. Humans have always wondered about boundaries, about what lies beyond the known, about whether space extends infinitely or has edges. Our ancestors wondered about the edge of the world, about what held up the sky, about whether stars were distant suns or something else entirely. We wonder about event horizons, about parent universes, about the global topology of space-time. The specific questions change as knowledge advances, but the fundamental posture of wonder remains. We look up, we ask, what is all this? We seek to understand our place. Whether we're in a black hole or not, this impulse to understand, this capacity for cosmic curiosity, is part of what makes us human. The mystery we might not solve connects us to all the mysteries our ancestors faced, all the unknowns that future generations will encounter, and perhaps there's even beauty in the possibility that some mysteries remain forever mysterious. A universe fully understood, fully mapped, with no questions left to ask, might be less inspiring than one with vast unknowns at its edges. The presence of mystery makes space for imagination, for speculation, for the feeling that reality exceeds our current comprehension. This isn't an argument against seeking answers. We should explore every question we can, test every testable hypothesis, push understanding as far as possible. But when we've pushed to the limit and uncertainty remains, we can hold that uncertainty peacefully. We can say, I've thought about this carefully, I've looked at the evidence, I understand the arguments, and I don't know. That's an honest, humble, intellectually respectable position. The peace in accepting mystery comes from releasing the need for premature certainty. It comes from being comfortable with questions that stay open, with understanding that's partial but real, with knowledge that's substantial yet incomplete. It comes from trusting that the inquiry itself has value, that the careful thinking about possibilities is worthwhile even when conclusions remain tentative. For our specific question, this means we can appreciate both what we know and what we don't know. We know the universe expands, we know its age and composition, we know the physics governing its evolution. We don't know if it's contained by an event horizon, we don't know if there's a parent universe, we don't know the ultimate global structure. Both the knowledge and the ignorance are real. Both are part of our current relationship to cosmic reality. And in that relationship, in that state of knowing and not knowing, we find our place, not as masters of all truth, but as curious beings asking genuine questions, sometimes finding answers, sometimes living with uncertainty. Always seeking to understand more while accepting that complete understanding might elude us. This is the human condition in a cosmos that's both revealing and mysterious, both accessible and hidden, both small enough to map in detail and large enough to contain unknowns that might exceed our grasp. As we prepare to bring our exploration to a close, let's think about what remains true regardless of whether we're inside a black hole. What aspects of our cosmic situation are constant across both possibilities? What can we be confident about even while larger questions remain open? First, the universe we observe is real. The galaxies, the cosmic microwave background, the expansion of space, the formation of structure, all exist whether we're in a standalone universe or a black hole interior. Our observations correspond to actual physical reality. The data we've collected, the measurements we've made, the patterns we've detected, all describe something genuine happening in space and time. This might seem obvious, but it's worth stating explicitly. The black hole universe hypothesis isn't suggesting that what we observe is illusion or simulation or fundamentally misleading. It's proposing a particular global structure that contains and contextualizes our observations, but the observations themselves remain valid. The physics we've discovered works. The theories we've developed predict observation successfully. The understanding we've built is real understanding. Second, the laws of physics we've discovered apply locally. General relativity accurately describes gravity and space-time curvature in our region. Quantum mechanics accurately describes particles and fields. Thermodynamics, electromagnetism, nuclear physics all work the same whether we're contained by an event horizon or not. Local physics doesn't change based on global topology beyond our observable region. This consistency is profound. It means that everything we've learned about nature, every principle and equation and prediction, remains valid and useful. We can continue doing physics, chemistry, biology, engineering, all the sciences with confidence that our methods work. The question of containment is about structure at scales far beyond what affects daily science or technology. Third, we exist and are conscious. Whatever the cosmic structure, the fact of experience is undeniable. You're reading or listening right now, thoughts are occurring, sensations are happening. This immediate reality of consciousness is certain in a way that theoretical structures about cosmology cannot be. The experience of being is the foundation on which all other knowledge builds, and with consciousness comes significance. Your experiences matter, your thoughts have value, your choices affect reality. Whether you're in a black hole universe or not, your life unfolds in real time, with real consequences, creating real meaning. The cosmic context doesn't diminish this. If anything, the vastness of cosmic uncertainty makes the certainty of immediate experience more precious. Fourth, we're connected to the cosmos through physical law and cosmic history. The atoms in our bodies were forged in stars. The energy driving our metabolism comes ultimately from nuclear fusion in the sun. The very structure of space and time shapes our existence. We're not separate from the universe observing it from outside. We're part of it, manifestations of its capacity for complexity and self-awareness. This connection holds whether we're in a black hole or not. Either way, we're made of stardust, products of billions of years of cosmic evolution, participants in ongoing physical processes that extend across billions of light years. We're locally concentrated complexity in a universe that tends toward disorder, temporary patterns that think and feel and wonder. This is true regardless of global topology. Fifth, the universe is comprehensible. The fact that we can understand it at all, that mathematics describes physical reality, that experiments confirm theories, that observations reveal patterns, all this is remarkable and remains true. We might not understand everything. We might never settle certain global questions. But the accessibility of the universe to rational inquiry is established. This comprehensibility isn't inevitable. We could have found ourselves in a chaotic universe with no discernible patterns, or a universe whose patterns are too complex for human minds to grasp. Instead, we can write equations that predict the motion of planets, the behavior of particles, the evolution of the cosmos. This workability of science holds whether or not we're contained by an event horizon. Sixth, the future remains open in important ways. We don't know what discoveries await, what observations future technology might enable, what theoretical insights might emerge. This openness to surprise, this potential for progress, exists whether we're in a black hole heading toward a singularity or in an infinite universe expanding forever. Our ability to learn, to adapt, to develop new understanding continues. This means the question of black hole containment itself might be resolved in unexpected ways. Perhaps quantum gravity will reveal that the question is ill-posed, that black hole interiors and standalone universes aren't really distinct categories. Perhaps new observations will definitively answer it. Perhaps philosophical analysis will show it's not as meaningful as it seems. The future could bring clarity we currently lack. Seventh, beauty and wonder remain available to us. A sunset is still beautiful whether we're in a black hole or not. Music still moves us. Art still speaks to us. Love still connects us. These human experiences don't depend on cosmic topology. They arise from how we engage with our immediate environment, how we relate to each other, how we create and perceive meaning. If anything, cosmic uncertainty might enhance wonder, knowing that we don't fully understand our cosmic situation, that vast unknowns surround us, that reality might be stranger than we imagine. All this creates space for awe. We look up at the night sky with appreciation for both what we know and what remains mysterious. Both contribute to the sense that existence is profound. Eighth, our actions matter. What we choose to do, how we treat others, what we create and preserve, all have significance within the universe as we experience it. Whether that universe is a subset of a larger structure or not doesn't change the reality of consequences. Helping someone reduces their suffering, whether we're in a black hole or not. Creating knowledge advances understanding, whether we're contained or infinite. This ethical dimension is independent of cosmic structure. Morality emerges from our nature as conscious beings, capable of affecting each other's welfare, from our ability to reason about consequences, from our capacity to care about more than our immediate self-interest. These capabilities exist regardless of global topology. Our responsibilities to each other remain constant across cosmic possibilities. Finally, the very act of asking these questions is valuable, that we can think about whether we're in a black hole, that we can explore the implications, that we can reason about possibilities beyond direct observation, demonstrates something important about human capacity. We're meaning-making beings, pattern-seeking minds, creatures capable of contemplating structures vastly larger than ourselves. This capacity persists whether we find answers or not. The question, are we in a black hole, joins the great questions humans have always asked. Where did we come from? What is this all? Why do we exist? What happens when we die? Some of these questions have found partial answers through science. Others remain open, but all of them reflect our fundamental nature as questioners, as beings for whom the world is not simply given but must be understood. So as we conclude this exploration, we can hold both uncertainty and certainty. We're uncertain about cosmic containment, about global structure, about ultimate boundaries. We're certain about local physics, about immediate experience, about the value of understanding. Both the uncertainty and the certainty are part of our cosmic situation, part of what it means to be conscious beings in a vast universe asking questions about our place within it. Thank you for staying with me through this long journey into one of the strangest questions we can ask about our universe. We've travelled together for 2.5 hours, exploring physics and philosophy, mathematics and meaning, observation and speculation. It's been quite an exploration, and I'm grateful you trusted these questions enough to let them unfold. We've covered so much ground, from the nature of black holes and event horizons, through the expansion of space and the evolution of cosmic structure, to the limits of knowledge and the peace found in accepting mystery. We've looked at Einstein's equations, at quantum gravity theories, at multiverse proposals. We've thought about what we can observe and what might remain forever hidden. We've contemplated what it would mean to be inside a black hole, and what stays true either way. The answer to our opening question, honestly and simply stated, is we don't know. We might be inside a black hole living in an interior region that will someday reach a singularity, or we might be in a standalone universe, expanding forever or finite but unbounded in ways we haven't determined. Both possibilities are consistent with current observations. Both are mathematically coherent. Both are permitted by the physics we understand. Perhaps future observations will settle the matter. Perhaps advances in quantum gravity will reveal that the question itself needs reformulation. Perhaps we'll develop new ways of probing cosmic structure that give us access to currently hidden information. Or perhaps this question will remain open, one of those deep mysteries that defines an era of human understanding without being resolved within it. And you know what? That uncertainty is okay. What we've learnt through this exploration isn't diminished by lacking a definitive conclusion. We've understood how the physics works. We've seen how different pieces of cosmology connect. We've thought carefully about the relationship between observation and reality. We've exercised our capacity for wonder. Before I say goodnight, I need you to know something. When this video was posted, most people scrolled right past it. They saw the length, they saw the topic, and they kept scrolling. But you didn't. You stayed for 2.5 hours, you chose depth over speed, and wonder over noise, and I think that says something beautiful about the kind of person you are. If this channel has given you something tonight, a little more peace, a little more wonder, a little more understanding of the world you live in, then a like and subscribe is the kindest thing you can leave behind before you sleep. Not just for this channel, but for the next person out there tonight who needs exactly what you just found here. Now, rest. You have earned it. We've exercised our capacity for wonder, for careful reasoning, for holding complexity without forcing premature simplicity. Wherever you are in the world right now, as these words reach you, I hope you found some comfort in this slow drift through cosmic questions. I hope your breathing has indeed slowed, that your thoughts have quieted even as they've expanded to contemplate vast scales and structures. I hope the complexity of what we've discussed has somehow felt peaceful rather than overwhelming, the uncertainty more freeing than frustrating. Look up at the sky if you can, or imagine it if you can't. See those stars, those points of light that are actually distant suns, some of them already dead, though their light still travels toward us. Each photon has journeyed for years or centuries or millennia to reach your eyes. That light is real whether we're in a black hole or not. The journey is genuine, the radiation authentic, the cosmos it reveals actual and present. All those stars, all those galaxies we've discussed, all that structure spanning billions of light years might be contained within an event horizon we'll never see, or it might extend infinitely in all directions, beyond any boundary, truly limitless. We float in this uncertainty, these tiny conscious beings on a small planet orbiting an ordinary star, asking questions about the largest structures imaginable. And somehow that's beautiful. Somehow the combination of our smallness and our capacity to think about such vastness creates something meaningful. We're the universe's way of wondering about itself, of asking whether it's contained or unbounded, of seeking to know what lies beyond the furthest reaches we can observe. This self-reflective capacity emerges from matter and energy following physical laws, and it's remarkable regardless of cosmic topology. If we are in a black hole, then every moment of beauty you've experienced, every connection you've made, every thought you've had, has occurred inside this structure. The universe has created complexity and consciousness within this confined space, has allowed for meaning and understanding to emerge, has permitted beings like you to ask these questions. That's extraordinary. If we're not in a black hole, if space extends infinitely or loops back on itself in some other configuration, then we're part of something even more vast than we've imagined, participants in a truly boundless existence. The universe stretches beyond our cosmic horizon into regions we'll never observe, and we're one local expression of its capacity for structure and awareness. Either way, you're here. You exist. You can think and feel and wonder. You can appreciate the night sky, can grasp the mathematics of space-time, can contemplate whether your universe is a black hole interior. You can experience the curious mix of insignificance and significance that comes from being a conscious being in a vast cosmos. That experience, that immediate reality of your consciousness engaging with these questions, is certain and valuable regardless of cosmic structure. Sleep well. Friend, let these thoughts drift through your mind as you drift towards sleep. Dream of stars if you dream at all, of vast spaces between galaxies, of light travelling through curved space-time, of horizons both visible and invisible. Dream of the universe in all its mystery and majesty, comprehensible yet containing depths that exceed our grasp. Whether we're inside a black hole or in an infinite universe, whether we're contained or unbounded, finite or endless, we're here together for this brief moment of cosmic history. We share this time, this space, this remarkable fact of existence. And in that sharing, in that common wonder about where we are and what surrounds us, we find connection. Thank you for exploring this question with me. Thank you for your patience with complexity, your tolerance for uncertainty, your willingness to think about the boundaries of knowledge. Thank you for caring enough about cosmic structure to spend these hours contemplating it. May you rest peacefully in the universe, whatever its ultimate nature. May the vastness comfort rather than overwhelm you. May the uncertainty feel like freedom rather than anxiety. May you find in the darkness behind your eyelids the same peaceful darkness between the stars, the quiet space where possibilities remain open and wonder never ends. Good night.